Hi, and welcome back to Synoptic Scale Weather Features. We are continuing our discussion of the different types of atmospheres. In a previous video, we looked at barotropic atmospheres, and we've also started looking at baroclinic atmospheres. Baroclinic atmospheres can be broken up or broken down or categorized into either equivalent barotropic or pure baroclinic. And we're looking at examples right now of equivalent barotropic atmospheres. Equivalent barotropic atmospheres means that the isotherms are parallel to the height contours, so there is no temperature advection. So looking at a weather chart, isotherms are parallel to the contours and there is no temperature advection. And we talked about in a previous video a special type of equivalent barotropic atmosphere. We talked about cold core systems. We looked at cold core lows and cold core highs. Now we're going to look at warm core systems. And there are a couple examples of warm core systems. The first one we're going to look at is warm core lows, or low pressure systems, and these happen quite frequently in the atmosphere. One place you'll find warm core lows is with thermal lows. And what thermal lows are, they're an area of relatively lower atmospheric pressure near the surface of the Earth that result from the heating of the surface of the Earth, and then the air in contact with the Earth becomes lower pressure and lower density. So this is what a cross-section of the thermal low looks like. At the surface, you can see that the 850 millibar line drops closer to the surface, so pressure right in the center of this warm core is relatively low. And then you can see on either side, the air is relatively cooler, and in the center, it's relatively warmer. So because the air is relatively warmer in the center, that means that the pressure surfaces are farther apart, and what appears as a low at the surface soon becomes a high at higher altitudes. And you'll see thermal lows very frequently during the summertime in subtropical locations, even over in the United States, the desert Southwest, where in Arizona and New Mexico temperatures soar into the 100-degree Fahrenheit range. You'll see thermal lows there all the time in the summertime. Now, these thermal lows really don't meander that much. They're not migratory weather systems. They're low pressure systems that result from the warm surfaces in those locations. And usually because of that, the circulations that you have with these thermal lows is pretty weak and diffuse. So here's an example of a thermal low. You can see across California, Utah, New Mexico, all these little low pressure systems, really weak low pressure systems. Those are all thermal lows. You can see that this occurred in August, and as a result of the strong surface heating, you get relatively lower pressure across California, Nevada, Utah region. And aloft, you don't really see a strong low pressure system. Actually, it looks like there's a little bit of a ridge across the desert Southwest. And that's what you normally expect. You expect to see higher heights in that region because of the hydrostatic equation, the thickness causing pressure surfaces to be farther apart in that warm air. Another type of warm core low is a tropical cyclone. And tropical cyclones is the general term that's used for low pressure systems or cyclones that develop over tropical oceans. And these are given many different names: tropical depressions, tropical storms, hurricanes, typhoons, cyclones also they call them. And these are warm core systems where at the surface you have a strong low pressure, and then aloft it weakens till finally you see actually higher pressure or higher heights at higher altitudes. So thermal or tropical cyclones really don't have any temperature advection. They're mostly driven by the release of latent heat through condensation inside the thunderstorms. So here's an idealized version of what a tropical cyclone looks like at 700 millibars. You can see that the temperature in the center of the low is very warm. You can see that the isotherms do not intersect the contour, so as a result there's no temperature advection. And of course, tropical cyclones, hurricanes are very intense low pressure systems at the surface, so you see some very strong convergence. But if you actually watch satellite imagery of hurricanes, you'll see that there's diverging air at higher altitudes. So here's an example. This is Hurricane Katrina back in 2005 across Mississippi, Louisiana, and also Alabama. You can see the counterclockwise circulation going up through the atmosphere. Here's 850 millibars, and you can see that there's a very intense low in the Caribbean. But then once you get up to 300 millibars, the low disappears. There's no strong low. As a matter of fact, the circulation is anticyclonic in that region. So that is a strong thermal low. Another type of warm core system, we covered low pressure systems. Now let's do high pressure systems. So we're going to talk about warm core highs. And an example of a warm core high is the summertime ridge that develops across the southeastern United States. And as you get up through the atmosphere, as you go up through the atmosphere, it strengthens with height. Here's a cross section of what I'm talking about. The center of this high pressure system is warm. It's high at the surface, but as you go up through the atmosphere, the height or the thickness between pressure surfaces is greater and greater, a great distance. So that means that at higher elevations in the atmosphere, much higher altitudes, you're going to find much higher heights for this weather system. So down low, you usually see at the surface a weak high and maybe even a low pressure system, kind of a thermal low perhaps. But up in the upper levels of the atmosphere, you'll find very strong ridges because of that warm air. So with a warm core high, you won't see any temperature advection. You'll just see isotherms that are parallel to contours. No temperature advection, but just really warm temperatures. Here's an example. Look over the southeastern United States. Here you see high pressure at the across Virginia and much of the eastern United States, very high pressure. And as you go up through the atmosphere, this is 850 millibars. You notice that there is a strong ridge in the east coast of the United States. And then finally, across the center of the United States, where there's very warm temperatures, you'll notice that this ridge really develops in the upper atmosphere. This is 500 millibars. And you've got actually a closed high at 500 millibars, a very intense high, higher heights up there. And that's a result of the warm temperatures. And this is what you typically find across the United States during the summertime. With you know, a very warm air outbreak across the region, where you have a heat wave. You also see really strong ridging across that area. So that brings to a close our discussion on equivalent barotropic atmospheres. In our next video, we're going to talk about purely baroclinic atmospheres.